So, we are having this course on risk conscious operational management of complex engineering systems, and now this module is on risk based engineering, and in risk based engineering this particular lecture will focus on risk based engineering framework. I am Professor Prabhakar V. Vardhe. So, when we talk about a framework, what it means? It means is we are showing only essential and necessary component, prominent component of particular area or function or activities or a software that we want to develop. So, it is basically a framework only. So, we have to see the salient feature of risk based engineering on this framework. Okay. Now, I will give you background. This particular topic I have taken up for illustration. You know, now you assume there is a complex engineering system, there is a plant, engineering plant, in which we are proposing some change. We are proposing some change because the expert in operations, they found that this practice is becoming expensive or rather resource consuming, and it is may or may not be required, or so can we have a solution like suppose certain safety provisions are there, they become prohibitive sometime, and if it is genuine thing that without compromising safety, if we can upgrade or increase our throughput, then the analysis is required. So, these situations, they are called changes, changes in the plant policy, changes in the plant configuration, changes in the inventory, resources, whatever. But at the outset, the safety should not be compromised, or even if it is compromised, it should be justifiable and it should be within the limit set by the regulators, or even the plant they can develop their own insight onto it, whether one should approach this change or not. Now, the de-risking in plant, always the effort goes on for de-risking, but sometimes only we have to make some change due to some constraint, and that's why we have to address the issue. And as the framework suggests, we have to first understand the requirement is the first step, then we have to do complete deterministic and probabilistic assessment. Okay, and therein the human factor should, because we discussed human factor plays key role in operational ecosystem, and then these two components, first they will provide an output, but before that there will be good transfer of events, transfer of knowledge, transfer of data will take place among these two, and finally we will have an outcome, and that outcome should be seen in the context of surveillance. That means whatever changes we are doing, they can be monitored either in terms of some process parameter or in terms of some process gain, output, or reduction in risk, and then these requirements you have to understand because we will be going to the next stage, that is where integrated assessment will be done and uncertainty will be characterized. So, what we are doing is, there was a requirement, we did a thorough and holistic assessment in induced human factor, or it was already there, we further qualified or weighted it, and then finally we went to cross check what are the requirement for surveillance and prognostics in the change environment, and then integrated risk assessment, uncertainty characterization. As I mentioned, it is an integral part of risk goals and criteria, and then finally we have to see whether it is in compliance with the set regulatory or performance goals. If everything is okay, then finally accept the change, what we want to do, whatever proposal was put up, we can accept it. But if the compliance are not being met, compliance means let's say regulator said had regulatory guides or documents or even technical specification of the plant, if it is not in compliance, or if we are changing the technical specification itself also, there can be some application for changing the technical specification also. Then we have to see whether it is complying with international criteria, national criteria, other criteria, and it is being demonstrated that there are no risk consequences or safety consequences. If they are there, then we have to again revisit our requirement and see that there are compensatory provisions that can be created, and further, and this is a iterative process till we get a yes and finally get an acceptance. So this involves risk characterization, integrated evaluation, performance metrics, because performance metrics is not only dealing with probabilistic metrics, it is dealing with the thermal hydraulic criteria, stress strength modeling, from structural point of view, human factor considerations. So all those things, and finally once the change is approved, then only it can be implemented. And there is again one more requirement: the change which has been implemented, it should be the feedback should be obtained on a period of 1 year or 2 years. This is a regular practice that one has to follow, that there is no undue consequences that the change is affecting. So we saw the broad feature of the framework. Now the most important thing is developing a definition and background why we want to do this and what we want to achieve. So the operations system can be divided into process system, safety system. These are the things we have been touching upon. It is just for the sake of change application that I am discussing. The process systems are required for continuous operation of the plant. The safety systems are required. They remain passive and standby. When a signal comes for their actuation, they will come into play, meet the safety function, and again go to the standby state. And since safety systems, they are normally 90% of the time they remain passive and in standby mode. Their testing is carried out periodically. It could be quarterly, it could be biannually, it could be annually, but they should be tested. Why? Because the latent failures which manifest into the standby condition, they should precipitate and corrective action should be performed. It could be maintenance action, it could be policy related issue, it could be new changes that we do, but it should be brought to the state where latent failures are less. And then even after doing that, now there is something called operating experience. Now if operating experience feel the latent failures, whatever testings are being done periodically, let us say quarterly, we are doing some testing for a system, let us say emergency cooling system, we are doing quarterly. The operator, they are experienced people, they can suggest, no, we are doing excessive testing, it requires resources, but the testing events are not revealing any major failure, latent fault, or even training related issues. Then the deterministic and risk based approach, they join together, and and then this change is affected. As I mentioned in the previous slide, that regulatory approval is required for affecting any change. Now this is a risk matrix, let us say if the normal core damage or damage frequency for a plant is, let us say, of the order of 10⁻⁻⁶. So this level, what is the freedom available to us if the plant frequency is, or it is called core damage frequency, it is a US NRC matrix that we have over here, where the acceptance criteria has been given. If it is more than 10⁻⁵, then this whole region become prohibitive. No change can be permitted. It is as simple as that. Now, if it is between 10⁻⁶ to 10⁻⁴, then you have to revisit what is our absolute frequency of our system. Then in this region only some changes are can be affected. But if it is of the order of 10⁻⁴, then we have very small availability, and here it becomes restrictive actually, So this shows the reason one, no changes can be affected. Reason two, some changes, and when our change in CDF is within this area, we can go up to this point also. So this matrix is sort of well accepted matrix, and this gives us a reference figure for absolute value of change. Let's say if we want to, in this case, we wanted to change the frequency of testing because over 15-20 years there was experience that it should be it should not be 3 months, it should go to 6 months. And that is what we approach with the regulator. So you carry out probabilistic analysis, deterministic analysis, because finally we have to ensure core cooling when we have an event of loss of coolant into the plant. Okay, so reducing the testing frequency is the objective, and then we are here to meet the goals and criteria. The challenge here is the basis of frequency reduction is very subjective and needs to a detailed engineering. So even though we can qualitatively we can express our opinion, but those justifications should be brought out in terms of scientific variables, okay, like uncertainty analysis, sensitivity analysis, and we have to prove that we can this proposal is a very sound proposal and it is acceptable. Follow up and feedback, as I mentioned, form part of it. Even if we have affected the change, the regulator might say that you have to go for a feedback obtaining on this performance of this system for another 1 year, 2 year, and if you find something you have to come back, So it is like this. And then let us, as I mentioned, we will try to discuss this particular subject with a simplified consideration and simplified schematics. So system, what we have is, let us say, first let us try to understand. I have shown a very simplified view. This is a reactor, and this is a isolation valve between reactor and emergency coolant system, injection system, and when there is some rupture or loss of coolant in this system, then what we have is, please see, I have not shown complete recirculation system here, but I have shown only the reactor here. So there is a cooling loop. In that cooling loop, if there is a rupture, then this system should automatically get activated, and these two pumps should start ejecting the coolant into the reactor, so that we do not have a situation of accident in this one. Okay. Now, as we come to the subject, the objective is this particular emergency core cooling system. It is a standby system, safety system, or we normally it is called as engineering safety feature, engineered safety feature. So in case of emergency, the cooling water from this pump 1, pump 2, they are injected based on the requirement. Later on we can operate 1 pump or 2 pump or both the pumps, but here the objective is we were testing this whole system along with many other associated components which I have not shown here, and this testing sometimes require time, so we lose the throughput of the system for which it was built, and that is number one. And number two, we are not able to discover by frequent testing, we are not able to have a huge safety insight in this. So there is a proposal to increase the frequency from 3 months to 6 months. By doing that, first thing we are doing is we are avoiding the aging of the components. Then second thing, we are having additional time when plant can operate, because without this system plant cannot operate. So if the system is blocked, then during testing this is the technical specification requirement. So it should be tested less frequently. Let us talk about 6 months. The system success and failure criteria, we have to discuss what kind of flow and all that is required, pressure that is required, okay, and then safety performance, cooling flow pressure, as I said, then threshold values we should know. So it is not only the probabilistic parameter. So now we have a PRA model of the plant, and on that PRA model this change will be affected, and we will see whether any change is there at the system level, that is safety system level, second at plant level, and if it is there, how much it is there, and then the case will be submitted to the regulator, and finally clearance will be obtained. So, what are the deterministic steps involved? We discussed there are probabilistic steps, deterministic steps. So, defense in depth should not be compromised, and identification of hazard internal and external. So, whatever changes are being done, it will be seen in the context of internal event, external event, and then the event frequency will be propagated on the safety model of the plant, and the formulation of design basis. Okay, it is required to have that it is not touching the safety violation of safety limits and design basis and all that. Identification of safety functions, this is very important. So, what are the any change when we do, what are the safety functions? Now, here in this particular slide we have become little generic, because what comes as a deterministic only we are discussing over here. Deterministic safety analysis involve thermal hydraulic analysis, structural analysis, hazard analysis, and formulation of safety acceptance criteria. It could be in terms of flow, it could be in terms of pressure, it could be in terms of thickness, or any physical parameter. So, those criteria have to be understood. Development of plant technical specification. So, the plant technical specification is a document which is derived from the safety document of the plant, and here there are a stipulation in terms of surveillance, in terms of maintenance, in terms of manpower, in terms of safety limit, that is threshold limits for safety, and then limiting condition for operations, and so many things. So, and this should not be violated. So, this document should be available, and what we talk about it change, we are talking about change in respect of technical specification. So, if you want to change the technical specification, that is from quarterly to 6 monthly, and so we have to demonstrate a case systematically. Identification of training requirements, regulatory clearance and compliance. These are the part of deterministic component into a plant system. Then probabilistic risk analysis. Probabilistic risk analysis, because we have been discussing deterministic and probabilistic, I am not going into the details of it, but then there is a separate lecture on deterministic and probabilistic where we will go into the detail. Now, in the framework I am avoiding those detailed or lengthy discussions actually. So, probabilistic risk analysis, if a plant has to have an intention to do a PRA analysis, a policy document should be there, that why it should be done, because PRA modeling is a very expensive proposition, and there should be justification, because manpower, resources, facilities, software, models, method, experimental facilities are required to support a PRA development program. Then most important step is identification of initiating event, and particularly this step will enable you to write a project report, giving all the justification, details, depth, scope of the document, objective of the document, and then we will have a list of initiating events, and this initiating event even form part of the deterministic approach also. So, a ready-made one set will be available, but we will have to have our own master logic diagram, learning from other plants and all, and then we have to update the initiating event list as part of the probabilistic risk analysis, and then the safety system modeling has to be done. We have seen many fault trees, how they are drawn, and then finally development of accident sequence and identification of human interactions, because we are talking about the risk conscious operation management ecosystem. So, what happens is, in this process, the way we saw in the risk based framework, lot of exchanges takes place between deterministic and probabilistic. Like from deterministic side, we have these are the input that can go to the probabilistic. It lists of applicable initiating event, plant and system configuration, thermal hydraulics, redundancy and directory, failure criteria or acceptance criteria, factor of safety, and plant layout and data. So, this they enable development of a PRA model of the plant, when we develop the PRA model of the plant, many input can be useful for deterministic analysis, list of initiating event. If we have updated and we have one or two event extra, that can go to deterministic side also. And for its assessment, plant SSC failure probabilities, what are the failure probabilities? So deterministic, we know which area to focus more or less. Safety system unavailability, this becomes which safety system needs modification and consideration from the deterministic point of view. Plant risk statement, uncertainty characterization. So these are the input, and what we have net output is risk based engineering framework. Okay. We discuss what are the requirement and salient feature of risk based engineering through the flow chart that was formed part of this lecture. Definition of it is not RBE, it is risk based engineering, because when it was this methodology was being developed, it was given a name integrated risk based engineering. Now it is only risk based engineering, and that's how the title of my book. Formulation of problem. We have seen how much effort goes into the formulation of the problem, what you want to do, major feature of deterministic and deterministic consideration through illustration we have seen, probabilistic features also included, and what we saw interface exchange of from risk based framework between deterministic and probabilistic, how it happens.